I
Yeah,
hope that is clear. Okay.
yeah.
So yeah, that is for reducing the computation. Now, once you have found out that E is the vector, then you come to the this one layer 0, final layer. Okay, and there you would find there are it is even more dense here, right? Okay, it will be even more dense, and now you will navigate in this denser area to reach the most nearest vector. Okay, maybe this is the most nearest vector. Okay, so you have avoided, like, there will be too many vectors right here, all this, it will be very dense. So we have avoided all those computations. We are
Hmm.
not checking our query vector with all other vectors. So we have picked up the sparse area, I mean, less denser area, and then finally we came to the, once we reached the nearest, somewhere near to the query vector, then we came to the dense layer and we navigated within that dense um, crowd of
Hmm.
vectors.
It's like when you have to send a parcel, you choose like which state to send to, then which city in the state,
Ah,
then which area
yeah,
in
yeah.
that city to send to, so that you can. If
Yeah,
you just give
exactly.
the area, not the city and not the state, you have to find like all the areas in the country and figure out, oh, this is the area. It will take so much
Correct,
computation.
correct.
So you narrow it
Yeah,
down like that. Okay.
you are not going to, yeah, you are not going to, what you say, card business and checking, okay, is this the pin code correct? And then you come to the Bellandur and check, then, so it's not like that, right?
Yeah, yeah, yeah.
So, okay,
Uh,
now let me search if I have.
that is how HNSW kind of helps us to retrieve the vectors close to the query vector. Okay.
Correct, correct. Okay. Can you guys see this? Okay, it's
Yeah.
just, you can see this, right? Okay.
Yes.
It starts in the top layer entry point, random entry point is selected. Okay. Then it does the greedy search, like out of its neighbors, who might be the closer to the query vector. Okay, until there are no close neighbors found. And then once all the neighbors are, the closest vector is found in that layer, you move to the next layer and repeat until the layer zero. You go until the layer zero. Okay, and once you reach there, where is that? Yeah, once you reach there, you pick the
Hmm.
top k results.
Hmm.
Okay,
Hmm.
here the query vector will not be there. Query vector I am just showing. Okay. Here the query vector will not be there in this layer 0 or
Hmm.
even any layers. That is just I'm showing where it falls. Okay. In the space. So you pick the nearest some 4 or 5, whatever top k is that, and
Hmm.
then you retrieve that and give it back to the as a retrieved chunks.
Hmm.
Okay. And
Can,
this
can
side
you go to
was
the
there.
same slide, please? This slide only. Just a second.
Hey, these things were not. I never saw this. Okay. Oh,
Oh,
this is the first time I'm seeing this slide. I don't know whether. Hmm.
These are bits slides, is it, Pavan?
Yeah, yeah, we are
Okay.
recording.
that's okay, man.
Okay.
We are
This is
giving
only with
the
us, right? This recording only between us, right?
Yeah, yeah, yes, yes. So
We'll not
okay,
be
these
posting anything.
slides
but there is
also
no
I'm not.
bits copyright mentioned here, no. But we'll give the credits to
No,
Yeah,
just
bits.
credit
for
to
my,
bits.
I
Yeah.
just wanted to know if Pavan has prepared or like
No,
from
no,
his
no,
course.
Oh,
That's
this
what I
no.
just wanted.
this is some next level stuff. Okay.
Okay,
Yeah.
okay.
No,
Okay.
I
Hey, Bhavan,
don't
Yeah,
know
share
whether.
these
continue.
slides, man. We'll keep it amongst ourselves only.
Okay. Okay, so I think I was looking for. Uh, Okay, this is part of approximate nearest neighbor. I was looking for the numbers which I can show you guys, okay, because that will bring some clarity to you. I don't know whether that numbers are here. I saw it somewhere.
Okay. So you
Where
search
is
the
the
numbers.
number?
Meanwhile, I'll just try to zoom out and come up, find a bigger picture here. Like, so all these
Yeah.
technologies of ANN, approximate nearest neighbor, they are for indexing your vectors inside the vector database or any data, or maybe any database, for instance. And different ANN is the generic name for the technology, and for the standard and technologies are like HNSW, Hierarchical Navigable Small World, or we have looked at we have there are some other technologies as well like IVF, inverted file. Then you mentioned something about PQ. Some PQ is also similar tech to segregate the vectors in such a way for faster retrieving the top K chunks. Right. So all these are like ANN technologies, right?
Yeah. So the
Hmm.
thing is that, okay, let me try if I can paste it here. Yeah. The thing is that these technologies are not used like single, like HNSW alone is not may not be used.
Hmm.
So it is used in the combination. The especially I think HNSW and the PQ is the most best combination, which actually gives the um, cost, which is actually cost effective because HNSW is memory intensive. Okay, it needs to, I think it takes more memory. Okay, so PQ is another, it is similar to the IVF only, PQ also, where clustering will be done. Okay, and
Hmm.
in that, within those clusters, you will search. Okay, the vectors itself will be divided into vectors itself will be divided, and
Hmm.
those parts of the vectors will be put into different clusters. Okay, that's a
Hmm.
bit that calculation is very complex actually. So
Hmm.
maybe if you want, we can talk that later also. But these things and all, you really don't need to know. I mean, good to know, but it's not like very much required for your daily work.
Hmm.
But HNSW, knowing the HNSW really gives you an idea that, okay, if you add 10 more vectors or 100 vectors, it doesn't really matter actually. You
Hmm.
understood,
Hmm.
right?
Hmm.
So
Hmm.
people
Hmm.
will say that, okay, people will say that, okay, you are having too much of vectors and that will become slow.
Hmm.
But at that time, they do not know actually that how this the HNSW works.
Hmm.
Okay, so it
Hmm.
doesn't become slow just like that. Okay, so
Understood.
if you see
Understood.
here, you have 10,000 vectors and you will have only 1,000 vectors in the layer one. You can have only 100 vectors in the layer two, and that will come to only 10 vectors. This is an example, okay, in the
Okay.
layer.
Like,
Now, if you put here 1 million or another three zeros, right? You can increase these layers. The layers will increase actually. It's not only four layers. It goes to six layers. Okay.
hmm. Hmm. Hmm.
So your
Hmm.
first layer is usually like very small numbers. It will have like 10 vectors only. Even if your end final number of vectors or total number of vectors is like billions, your
Hmm.
first layer, I mean top layer will have very less vectors.
These are like not the fixed numbers. No, this is just a way of conveying that by a factor of 10, the
Uh-huh.
layers will keep on
Yes.
decreasing the number of vectors. That's it.
Yes,
So
yes.
if I
This
have
is
like,
not the exact number. This is not the
ah,
exact numbers. This I just gave a sample.
hmm.
Okay. Yeah, you were asking something.
Yeah, I mean, if we have like 10 million vectors, and if we have maximum six layers possible, then 10 million, then 1 million, then 10,000, then 1,000, then 110. So by factor of 10, they keep on decreasing. That's it. The factor of 10 is standard or?
No,
Just
no,
for
that
example.
factor of 10 is not standard, I think.
Hmm.
Um, that that even I have those, I think those calculations are complex, so I don't know. Okay, what did you ask? What do you want me to ask? What is the formula to calculate the vectors in each layer? And so it, uh,
ChatGPT Enterprise by Altimetric. Nice. Which model it is?
yeah,
5.5.
this is 5.4, I think. Okay, so vector count per layer is defined by the total number of vectors and the number of connections each vector will have, that is m, to the power of which layer it is. Okay, and that is how the total vector is calculated. And ml is the decay factor.
Hmm.
So it will be 1 by
Natural
ln
log
of
of
m.
M.
Yeah,
Hmm.
natural log of m. Yeah.
Hmm. Hmm.
Hmm.
Okay.
I think this is not the actual formula. I guess the actual formula is more complicated. This is like they have said, no, like almost equal to
Almost
kind of.
equal to, yeah. Equivalent
Yeah,
to,
yeah.
yeah. I see
Yeah.
here,
So
it is not a
yeah,
factor
this is
of
the
10.
this yeah,
Hmm.
this is the this one. If you have n vector like how much 10 lakh vectors here, your
Hmm.
next layer will have 62,500. Next layer will have 3,900 and 245 and 15. So your
Hmm.
final layer will have very less actually.
Hmm. 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 Nice. Okay. So
And
N.
one more thing I wanted
Hi.
to say, okay, I
Hmm.
think this many people do not know.
Hmm.
Uh, okay, so what I wanted to say was, I mean, just an information.
Hmm.
Um, See, when you say, how do you find the nearest neighbors? Sorry, I mean, how do you compare the query vector with the vectors in the vector DB before you retrieve them or give that back to or retrieve it back? You will say that we are doing the cosine similarity, right? But actually, there
Hmm.
are two more things which happens. Two more, or at least one more thing will happen. So there is something called Euclidean distance.
Euclidean distance. Okay.
Yeah, you might know that, right?
Hmm. I know the term. I forgot the meaning of it. So it is so
Uh,
HNSW is a different. So cosine similarity is one way to retrieve the closest neighbors. One of the technologies of ANN. One of the ways to implement ANN, right? And HNSW is the other way to implement
no, no.
ANN. It is not.
No, 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 no. Cosine similarity is it's a general thing, right? A general calculation, or the Euclidean distance is also general calculation. Yeah, HNSW, ANN is the blanket method.
Hmm.
HNSW is one kind of ANN, and
Hmm.
HNSW can or will use the cosine similarity while
Distance between
mm,
the vectors.
finding the distance between the vectors.
Oh,
Yeah,
okay,
right.
okay, okay.
And the thing is that it is not only the cosine similarity which it is being used.
Hmm.
So why am I saying is that, so what does the cosine similarity does? So cosine, you have two vectors like this. Cosine similarity finds the angular deviation between the two vectors. Okay,
Hmm.
I would take my words all in the sense that I might be wrongly sounding in the sense using the words. Okay, don't take it like, okay, I said exact this word. I might be
Gold truth. Okay, we'll not take it as a
may not
gold
be
truth.
correct also. Okay,
Yeah.
so so it actually finds the angular separation between the two vectors. Okay, so this is your vector here, this
Hmm.
is your vector here. So it
Hmm.
finds the angular how much. how much they are away from each other, okay, in the
Fine.
angular space,
Hmm.
okay. But your Euclidean distance actually finds the distance between the two vectors itself,
Hmm.
okay.
Hmm.
They
Hmm.
are two different things.
Hmm.
Um, so the formula is this one, okay.
Hmm. Hmm. Hmm.
Uh, if you are in two-dimensional space, it's x2 minus x1 whole square plus y2 minus 1 y1 whole square and
Fine.
the square root of it. That is the Euclidean distance.
Yeah.
Okay. The cosine similarity is using the dot product.
Okay. X1 dot Y1
Okay.
plus X2 dot Y2.
So cosine similarity, uh,
X1 dot X2 plus Y1 dot
this,
Y2.
yeah, A into B dot product and magnitude of A divided by magnitude of A into magnitude of B. So this is actually gives you the angular separation. Okay, it
No.
won't. So that was a question. I suddenly got it, and then I asked. Let's ask here only. Does HNSW uses only
Cosine
cosine
similarity
similarity?
or Euclidean distance, right?
Yeah.
Hmm. But then cosine similarity is not an effective way to find the nearest neighbors, right? Because even if the angle between them is less, they can be far apart in terms of Euclidean distance, right? Then they can be in
That's
different
what
cluster altogether. Yeah.
exactly. So here, see here, the magnitude of vectors is different. Suppose there is one
Yeah.
more vector here. Okay,
Hmm.
these two
Oh,
vectors, and these two vectors will have the same cosine similarity, right?
right, right.
Yeah. Yeah.
No,
But
but
yeah, yeah.
but they're divided by your magnitude of the vectors as well. In the formula, you do in cosine similarities. The formula
Uh-huh.
that you showed above, you
This one,
have the
right?
a dot b. This is multiplying the two
But
vectors. Say if it is
correct. But
two-dimensional vector, it is like what is shown below, multiplying like a1 with a2 plus b1 with b2 and so on and so forth, and divided by magnitude of vectors.
see,
So that
yeah.
yeah,
No,
magnitude
no,
of vector.
I understood what is your this one, but still, this is not the Euclidean distance, right? Even though you are dividing this by the magnitude, this is not the same as Euclidean distance. This is still gives you the angular that separation only.
Yeah, even if vectors are on the same line, like same extension, like you draw in that picture, right? For those two vectors also, they'll not have same cosine similarity because the magnitudes are different, and we are using magnitude also in the calculation of
No,
cosine similarity.
no. That you are dividing it here, right? So that will have the same, I think. Cosine similarity between these two things will be same. Okay.
Between what two
Let's
things you are saying? What two things you
so
are saying?
I am saying let's say A, B, C. So A and C and B and C, those cosine similarities should be same. Will the cosine similarity be same for A, B and AC?
Cos theta. My God, trigonometry. Forgot.
Yeah. See, this is the one. Cosine similarity will be same for A and B and A and C. Cosine similarity will not be able to differentiate the magnitude. Okay.
Between A and
Hmm.
B, it is the same. And between A
Same
and C
cosine because
also.
it only takes
Theta.
the
The
uh,
theta.
Angle,
angle. Yeah,
not
angle.
the distance.
not the magnitude.
Because B
Okay,
and C are on the same line, right? So it will be the same. It will consider it as the same. The angle is the same, no?
right.
No, the angle is the
So,
same. That is okay. But but the formula that we saw for cosine similarity, that involved the
yes,
magnitude as well. And since
no,
the
no,
B
that
and C, they have different magnitudes.
see, this is not the same as the this is your kind of normalizing, I think. Okay, I'm not a mathematics.
But that's okay for the sake of
No, no, but I
understanding.
think. I think we can check this again further in the this
Hmm,
and understand it better, okay? Because these are the like basic things. So, but the
hmm,
one thing what I can tell you is that see here, even though you are giving the magnitude, you are saying that you are dividing it by the magnitude, or even the A and B has the magnitude, still it is a dot product. Here in the Euclidean distance, it is not the dot product.
hmm,
Okay, I mean it is a completely different.
hmm, hmm, hmm.
So this particular dot product will not give you the in the sense what you say. I don't know. I'm thinking like it will not give the spatial distance. It only gives you the angular, it only considers the angular factor. But I understood what you are trying to say.
Yeah,
I may not
okay.
have the exact
But
answer there.
But for
Uh,
the ease of saying, we
but
can say that if two vectors they lie on a same angle with another vector, then its cosine similarity is the same across, yeah, both the ways. Yeah, understood. I got the point, but we don't need to go into that depth for now. We can look at it some other good time. Yeah, that's fine, man.
I'll just check. Cosine similarity still uses magnitude in the formula. How it is not able to count on the or is a very common point of confusion. You are completely right about the magnitudes given. However, they are placed in denominator. They are placed in the denominator for a specific reason to cancel out the effect of the vector lengths. Formula uses magnitude specifically to normalize the vectors.
Okay, they strip away their magnitude so that only the direction remains. They are only focusing on the direction, not the magnitude. Even the magnitude is there, it is normalized, it is removed, it is stripped out of
Yeah, it
the
is.
calculation.
Yeah, it is right. It is only finally you will be only getting that angle of it.
Yeah.
Yeah.
Magnitude of A is this. It is like this, B is this. Similarity between A and B, they divide 8 by that and okay. A और C का डॉट प्रोडक्ट is 16. A इतना B इतना डिवाइड करता है ये इसको तो फिर इसके पास आ जाता है.
Yes. See, this is
Hmm?
what it is. Okay. HNSW can use the Euclidean distance as its metric. In fact, Euclidean distance is one of the most common metrics used with HNSW. When
Hmm.
you configure HNSW, it is the changes are. But whatever I saw before, it said that it can use both. Okay, cosine similarity and Euclidean distance, and that makes more sense to me using both. Okay.
Can you check if it can use both?
Yeah.
Sorry.
So yeah, I think this is something which oh you should not use both at the same time for HNSW.
Wondering like how it will choose one if it has to how it will use both.
No, no,
From
no.
what?
Using both is not a difficult thing. I mean, can you
But
Euclidean purpose?
how? Don't know.
Just give me a second. Let me see because I thought okay, can HNSW use both? Similarity and Euclidean distance.
Your data's meaning is defined by the relationship between features, not the total count or size of that.
See
Okay.
that this guy is saying,
You're sharing
mm,
something? Okay.
yeah, I'm sharing now. See, this guy is saying that yes, HNSW can absolutely use both Cosine similarity and Euclidean distance. In fact, they are the most common distance vectors used to build. Use both at the same time on the same index. This makes more sense to me. Okay, I don't know why.
Both at the same time on the same index. What do you mean
What
by
man?
that?
Oh, this is correct. This is correct. Both at the same time at the same index. That is correct. Because see, if you where is that?
What is
Okay,
index here?
index is where that vector is stored.
Oh, in a plane where it is stored. That is the index. Huh?
Yeah, that index
Indexing is
thing. I
like
think in I don't know
mapping
why
out,
Gemini
right?
is giving two different answers. Okay, what I was trying to say here,
But
right?
yeah,
Here, oh, this went off. Oh, okay, this went off, man. Okay, so what
do
we were
control Z,
discussing.
no? Control Z, remove it. It will not come.
No, it's not coming. Oh, it's okay. So in the plane,
Yeah.
we had like this vectors, and we had query vector here, right? So when you find the distance between this and this, okay,
Hmm.
when you find the distance between this, you can use the cosine similarity here. You can also use the cosine similarity plus Euclidean distance as well, right? To
How will you
check
use
which
both?
one is.
Like, how will you use both?
How will you use both? That I don't know. Maybe there might be some way. There is one thing called mean reciprocal rate. Okay, that actually
Hmm.
like merges the output of two different metrics. So something like that. These guys might have used. These guys might use, right?
Mean
But it is.
reciprocal rate is used as an eval for the RAG pipeline, right? Like for checking if the vector DB is giving the results what we want to have,
No,
and
no, no,
that
no.
is what
What I
it
was
is used for.
saying, no. I was talking about this hybrid search where you have the keyword search and also the dense search, right? That is cosine similarity search. So you can, if you do the two searches, keyword search and the cosine similarity search. Now you have two
Hmm.
outputs. How will
Hmm.
you, uh,
That
how
is
will you compare it and get the best out of it?
that is recall you're talking about. Recall at K, right?
Not recall it K. RRF? No, wait. What is
No,
that?
these what you mentioned, right? Keyword based check that is used. That is one of the variants of recall at K. And MRR is
Reciprocal rank fusion. Sorry. What did I say? Mean something
reciprocal
is it,
rate.
right?
That is to
No.
eval
Reciprocal rank
indexing.
fusion. RRF is
I
the
don't
one I
know the
was talking.
RRF. What is that?
That is like when you say you know about the hybrid search, right? You will have the in the RAG. You don't only do the uh, this what is that cosine similarity. Okay, say we are doing the vector search using the cosine similarity. Forget about HNSW also. We
Hmm.
might do it with other things also. So we do the cosine similarity search. This is called dense search. Okay,
Hmm.
dense search, and this is I shit man, I'm
Oh,
forgetting so many things.
BM25. That is like your
This
DF, IDF, and BM25. These are your what algorithms are these? Keyword search algorithms only. These are no.
correct. This is keyword
Yeah.
search. This is based
Mm-hmm.
on the keyword search, specific
Mm-hmm.
keyword searches. Okay. So
Mm-hmm.
now this BM25 will give you some output values, and
Mm-hmm.
this vector search will give you some output values. How will
Hmm.
you? how will you now? You have now 6 documents here, right?
Hmm.
You have 6 documents here.
Hmm.
So how will you select the top 3 out of these 6? That is where this RRF comes into picture.
Mm-hmm. Mm-hmm.
Okay, that is the formula.
That is
I
for
thought,
hybrid search only.
that means yes, sir. If you are using both, it is a hybrid search. If you are using both keyword and vector search, that means that it's a hybrid search. Okay.
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 I think
What is the full form? Reciprocal rank fusion. So you're fusing two
reciprocal rank
results
fusion.
and trying to find which is the best chunk
Yeah.
to use. Oh, okay, like
Yeah.
that.
Hey, just
Nice
give me a
one.
second. Just give
All
me a
right.
second.
All right, man. Pinakini, you're also impacted.
Not yet, Vinal.
Good, 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 actually.
Hey, Vinnal,
Yes, man.
and Pinakini. Hey, sorry, I need to drop now.
All right.
Is it okay? We can connect tomorrow evening. I'm there today evening, but you are not there, right? But one thing, let me know what are the things okay to um, go up on. Otherwise, I can also pick few things and
Pavan,
come.
one
Yeah.
question. So all these internals, right? So I am calling these as internals. So this is like for our understanding, or like outside people do ask questions on these, like what
Oh,
is
this.
the
Yeah, they
hmm.
might ask interviews. They can ask actually these things.
Oh, is it? Okay,
Yeah,
okay.
yeah, they can
Mm-hmm.
ask.
Like,
Okay, so
yeah.
yeah,
Okay, Pawan, you carry on. Then we'll schedule a time tomorrow.
Mm-hmm.
Tomorrow evening, we'll schedule some time.
yeah, I am fine with that. I suddenly have to go
Or
right
okay, man.
now.
All righty. You
Okay, okay.
carry
Yeah.
on. You guys
Mm.
will schedule a new timing for tomorrow. Okay.
Okay,
All
Vinay.
righty.
Mm.
Thanks,
Yeah.
Okay.
thanks,
Thank you, guys.
Pinaki.
Yeah.
Mm.
Bye bye.
Yeah, thank
Bye.
you. Bye. Yeah.